Hello my friends and welcome back to the You Can Do TV channel. The expansion of the Gleenom tunnel involved constructing a second 8.3 kilometers long eastern tube using conventional drilling and blasting methods. Excavation began in December 2013 at the north portal and in January 2014 at the south portal, progressing simultaneously from both ends. Cross passages were also excavated to serve as emergency exits. Meanwhile, concreting of the inner linings started from the south, using two shift teams to achieve around 25 meters per day. The interior construction included the lining, intermediate ceiling, emergency bays, and ventilation niches. Up to 800 cubic meters of concrete were used daily. After completing the lining, road pavement, LED lighting, and safety systems were installed. The MRT Malaysia SBK line tunnel breakthroughs marked major milestones in underground construction. Using tunnel boring machines, engineers excavated soil and rock to create twin tunnels beneath Kuala Lumpur. As each TBM advanced, segments were installed to form the tunnel lining. Once a TBM reached its designated endpoint, a breakthrough was celebrated. The first breakthrough occurred on December 24, 2013, followed by others including Breakthrough 2 on January 9, 2014, and Breakthrough 3 on January 16, 2014. Later breakthroughs, such as Breakthrough 7 on October 16 and Breakthrough 12 on April 11, 2015, demonstrated continued progress. Each successful breakthrough confirmed precise alignment and marked the connection between tunnel sections, ensuring safe and efficient construction for the MRT system. The Lake Mead third intake tunnel excavation commenced with the sinking of a vertical access shaft exceeding 600 feet in depth using the drill blast muck cycle. Workers utilized percussion drills to bore blast holes into the shaft wall, then inserted explosive charges. Following detonation, mucking operations removed fragmented rock using large buckets, each with an 8 cubic yard capacity and a loaded weight of 35,000 pounds. Excavation proceeded continuously for over a year until the full depth was achieved. A starter chamber and launch tunnel were then excavated at the base to house the tunnel boring machine. In June 2010, the excavation encountered a critical inflow event when 6,600 cubic yards of water-saturated mud and gravel surged into the starter tunnel. This inflow was traced to vertical fault lines acting as hydraulic conduits. The TBM launch was delayed by over a year while engineers redesigned the alignment to bypass fault zones. The 900-ton Heron Connect built TBM, designed to withstand up to 15 bars of hydrostatic pressure, was assembled at surface and lowered into the shaft with only 1 to 4 inches of lateral clearance. The machine featured dual-mode operation, open mode for competent rock and low inflows, and closed slurry mode utilizing bentonite suspension for unstable or water-bearing strata. Excavated material was conveyed by a screw conveyor and belt system. In closed mode, slurry pipelines transported spoil to surface separation plants. Throughout excavation, precast concrete segments manufactured off-site with a dimensional tolerance of 1.5 millimeters were erected to form the tunnel lining. Over 14,000 segments were installed, creating gasketed rings capable of resisting extreme hydrostatic loads. Simultaneously, marine crews offshore excavated a 60-foot deep pit in the lakebed using controlled underwater blasting. The 1,400-ton intake structure was suspended from strand jacks on barges and lowered precisely. A world record underwater concrete pour followed, delivering 11,000 cubic yards of high workability mix over 11 continuous days using a 350-foot tremie system. Extreme face pressures and abrasive conditions caused premature cutter head failure, requiring on-site refurbishment. After 3 years of excavation under pressures reaching 14 bars, the TBM broke through into the intake shaft. The tunnel was flooded and equalized before the bulkhead was removed, completing one of the most demanding high-pressure tunneling operations ever executed. Excavators are driven onto the ro-ro vessel via a ramp and secured using chains and wheel stoppers. Workers ensure proper alignment and stability. Once loading is complete, the ship departs. At the destination port, excavators are unchained and driven off the vessel using another ramp. The process of lifting and placing concrete pipes begins with a hydraulic excavator equipped with a varactored pipe layer attachment lifts and places concrete pipes efficiently. First, the operator aligns the machine with a pipe lying on the ground. The pipe layer's padded leg is inserted into the pipe's opening, ensuring a secure grip without damaging the surface. Then, the excavator gently lifts the pipe and maneuvers it toward the installation trench. With precise control, the operator lowers the pipe vertically into position, aligning it with the previously laid segment. The process is fast, safe, and eliminates the need for manual handling or slings. This method increases productivity and ensures accurate pipe placement on construction sites. A yellow Volvo wheel loader lifts a 28-ton stone block with its front bucket at a quarry. As the stone gets so heavy, the wheel loader lifts both rear wheels, but the operator is still able to carefully steer the machine and safely place the large stone block onto a transport vehicle. The machine demonstrates its strength, stability, and precision in heavy-duty operations in harsh mining environments. The bored pile drilling process begins with the rig precisely positioning itself at the marked location. A large twist drill then rotates and penetrates deep into the ground, efficiently cutting through soil and hard rock layers. The hydraulic system provides strong torque and downward force for effective drilling. As the drill reaches the designed depth, it is gradually withdrawn, carrying the excavated material to the surface. Afterward, the pile placement process starts. The machine accurately aligns the pile above the drilled hole and slowly lowers it into position. This ensures that the pile is securely and correctly installed within the drilled shaft, forming a strong foundation. Installation of a 14-ton pre-tied steel wall at the Back River wastewater treatment plant site. The wall was lifted and positioned by crane, precisely aligning with previously installed structural members. Workers guided and stabilized the wall section during installation. To connect the 14 vertical rebars, HRC 500 series couplings were used. These mechanical connections allow for a quick and secure connection between the pre-installed rebar and the in-situ rebar. Once positioned, the wall was lowered into place, and workers made final adjustments to ensure proper alignment. Workers hand-torqued the couplings to secure the rebars together. Known for exceeding A706 and A615 steel performance standards, the HRC 500 series couplings ensure a tough, high-strength connection capable of withstanding seismic and cyclic loads. This procedure demonstrates the efficient installation of heavy precast reinforcement members with reliable and consistent bar joints in the field. The project begins with the construction of a massive concrete dam across the river, creating a reservoir to store water. From here, intake gates control the flow into large penstock pipelines, channeling water under high pressure to turbines housed in the powerhouse. The turbines spin powerful generators, converting hydraulic energy into 850,000 kilowatts of electricity. After generation, switchgear systems regulate output, and transformers step up voltage for the transmission grid. Finally, the plant is integrated into local and regional networks, supplying clean, renewable hydropower to homes and industries. At Alcoa's Warwick operations, the smelting process begins in the green mill, where carbon anodes are made from petroleum and metallurgical coking byproducts, pressed into 900-pound blocks. These anodes are baked in a ring furnace at 2,000 degrees Fahrenheit for 5 to 6 days. Each pot in the smelter uses 26 anodes, replaced every 20 days with 190 anodes changed daily. Alumina, shipped from Australia or Brazil, is conveyed to pot rooms mixed with molten cryolite and charged with 130,000 amps. This separates aluminum from oxygen, with molten aluminum sinking to the pot's bottom. 2 pounds of alumina yield 1 pound of aluminum, producing over 300,000 pounds daily per pot line. The molten aluminum is siphoned into crucibles via tapping, impurities are skimmed, and it's transported to the ingot department for casting. The steel production process begins with blooms delivered from the continuous caster and stored in designated bays. Using a Viec crane, blooms are loaded into soaking pits and heated to target temperatures based on grades such as 1,275 degrees Celsius for tire cords. Once soaked, the Viec transfers blooms onto an ingot buggy and then to the pusher, which feeds them to the mill line. The blooms pass through a weigh station and enter the primary reversing mill, followed by the secondary mill, both reducing the bloom's size. For high-grade materials, inline scarfing removes surface defects. Cropping shears trim defective ends before the bloom enters the continuous mill, comprising roughing, intermediate, and finishing stands. Alternating horizontal and vertical rolls shape the product, while calipers monitor dimensions. A flying shear cuts the billet to customer-specified lengths. Billets then pass an inline stamping station and are cooled on banks before immersion in water tanks. High-grade billets proceed through automatic inspection, starting with roll straightening and shot blasting, followed by defect detection via the thermomatic system. Bars with defects are marked for grinding using high-speed rotating stones. Final inspection includes ultrasonic testing for internal flaws, particularly for hydraulic-grade steel. Bars are color-coded by chemical composition, then dispatched via rail or truck after being weighed and strapped. The facility processes up to 20,000 tons weekly, with a storage capacity of 50,000 tons for finished billets. After being shifted to the cooling bed, rail segments up to 78 meters long undergo pre-bending to reduce internal stresses. Once cooled below 65 degrees Celsius, they are straightened both horizontally and vertically using disc straightening machines. Straightening parameters are centrally stored, and each rail is measured at the measuring center. The axle production process begins with cutting the raw material, followed by heating before forging. The hot metal is then forged into axle shapes. After forging, alignment is checked before heat treatment. The axles are cut with a double saw and undergo impact, tensile, and spectrograph tests. Microscope analysis ensures internal quality. Centering machines prepare the axles for rough machining. Finally, the machined axles are stored for later use. The glass bottle manufacturing process begins with preparing raw materials including sand, soda ash, limestone, and cullet. These are accurately batched and mixed to ensure consistency. Next, the mixture is melted in a furnace at around 1,600 degrees Celsius, producing molten glass called gob. The gob is formed into bottles using either the blow-and-blow or press-and-blow method, depending on the bottle type. Formed bottles are then transferred to an annealing layer where they are reheated and gradually cooled. Quality checks are conducted to detect defects like thin walls or deformation. After passing inspection, surface treatment is applied. Finally, the bottles are carefully packed and delivered using proper methods to avoid damage during transportation. The heated metal billet is removed from the furnace, then placed under a giant hammer forging machine where it's struck repeatedly to form a rough shape. Next, it moves into a closed die forging press which precisely shapes the connecting rod. Finally, workers stack the forged rods, readying them for the next production stage. The casting process begins with the preparation of a sand mold and a carbon dioxide hardened core. A Mac wheel pattern is placed inside the molding box and covered with sand by the worker. After the sand has been compacted and covered the outer rim of the wheel pattern, the worker uses a nail to poke small holes around the surface of the sand that has just been covered. The core is made from a mixture of silica sand and sodium silicate. These cores are shaped in the core box and then hardened by blowing carbon dioxide gas through them. The carbon dioxide reacts with the sodium silicate, rapidly solidifying the core to form a strong inner cavity. Next, the core is placed into the mold cavity, and the mold halves are clamped together. After ensuring proper alignment, the molten aluminium alloy is poured into the mold through the gating system. The molten metal flows into the cavity, completely filling the space between the mold wall and the inserted core. Once solidification is complete, the sand mold is broken to obtain the raw cast wheel. The carbon dioxide core is also removed during this process, leaving the desired hollow features inside the casting. The casting is then surface cleaned to remove sand and oxides, followed by trimming to remove excess material such as risers and gates. Finally, the aluminum Mac wheel undergoes post-processing operations such as machining, surface finishing, and quality control to ensure it meets dimensional and performance standards. This carbon dioxide core sand casting method is effective in producing complex, hollow aluminum parts with good dimensional accuracy and surface quality. The Zenith 1500 fully automatic concrete block making machine operates on a pallet system and incorporates advanced German engineering to produce high-precision, high-volume concrete blocks. The concrete block production process begins with raw materials of sand, stone powder, gravel, waste, fly ash, and construction waste stored in 4 to 6 mixing tanks. An automatic dosing system measures each ingredient in proportion. The aggregates are lifted through a bypass hopper to a twin-shaft mixer for mixing of the base and top. Metered cement and water are added using real-time moisture sensors to ensure even mixing. The homogeneous material is transported by conveyor to the machine's hopper, which is monitored by a laser probe to ensure adequate material. The machine employs a servo-controlled vibration system with dynamic frequency adjustment, using rubber buffers and airbag dampers to minimize frame stress while maximizing compaction. The upper head vibrator with DC braking increases density for superior product strength. Molding precision is achieved via closed-loop hydraulic systems with contactless displacement sensors controlling the pressure head and mold frame positioning. The mold change system enables tool replacement within 10 minutes via an electric chain spreader, rotating head mechanism, and airbag-locked mold frame to ensure alignment and vibration efficiency. Formed products are transferred on large pallets by a hydraulic pitch track feeding system to the elevator. A frequency-controlled finger car, featuring a rotating centering system, transports the green blocks into the curing chamber and retrieves them post-curing. The system includes derailment and collision protection sensors. After curing, the blocks are transferred through a dry-side conveyor system composed of pitch-controlled horizontal and vertical conveyors. A pre-cubing system arranges layers for the cuber, which stacks them onto the cube conveyor. Rotation of layers 90 degrees, 180 degrees, 270 degrees is supported for optimal palletizing. All axes are digitally measured for path optimization. Used boards are automatically cleaned, flipped 180 degrees to prevent unilateral wear, and returned for reuse. Final product stacks are conveyed and transported to storage by forklift. Mold versatility enables production of various concrete products, including pavers, hollow blocks, and curbstones. In 2021, IGM welding robots performed a wide range of automated welding and material handling tasks across multiple industries. Central to the operation is the RTE400 robot, controlled by the fully digital RCE system and programmed via the K6 Teach Pendant or offline software. Robots worked with various welding processes, including GMAW, GTAW, PAW, FSW, and RSW, while integrating power sources and peripherals through a digital bus network. Position corrections were made using gas nozzle tactile sensors and laser systems. Offline programming enabled cycle time checks and collision prevention. Robots were mounted on tracks or portals to cover large components and used rotary tables or multiple axis positioners to extend work zones. These systems welded parts for excavators, railway vehicles, ships, gantry cranes, and forklifts, achieving high precision and repeatability even in demanding conditions like thick materials or distorted seams. IGM's modular solutions ensured flexibility and quality across all operations. The robotic welding process for excavator buckets begins by selecting the welds and setting the welding parameters in the ABAGY system. This includes defining the type of weld, its length, and other necessary data. Once the welds are specified, the robot scans the actual bucket to compare it with the uploaded 3D model, detecting any deviations in real time. This scanning step ensures that the robot can accurately adapt to differences in shape or alignment between the model and the physical part. After scanning, the system automatically generates the welding path without manual programming. The robot then performs the welding, following the defined parameters and adjusting its movements as needed to maintain high precision. This automated approach enhances both quality and speed, reducing the risk of human error. Throughout the process, the robot operates continuously with consistent weld quality, even on complex or non-standard geometries. ABAGY's adaptive control ensures that each weld is applied correctly, despite any variations in the bucket surface. Overall, the system allows for a streamlined and highly efficient welding process, transforming a traditionally labor-intensive task into a smart and flexible automated operation. The CHKPZ wheel plant includes profiling, stamping, rim forming, and wheel assembly lines, welding and 3 painting lines, electrophoretic, airless spraying, and powder coating ensure durability. The newest bay features advanced machines like RTM125, HAAS Machining Center, and a robotic turning complex. Processes meet TS 16949 standards with full traceability and Kaizen principles, enabling efficient production of over 150 wheel types annually. The LPG cylinder welding process using Repcon machines begins with MIG/MAG welding used to secure the foot ring and valve guard ring to the cylinder body. This method ensures deep penetration and a uniform weld. Next, submerged arc welding is also used to attach the valve head to the upper half of the cylinder. The system uses an automated welder equipped with a reliable power source and controller to maintain consistent weld quality and meet production needs. Submerged arc welding is then performed on the longitudinal weld machine, joining the 2 halves of the cylinder body. These welds are performed with precision, ensuring structural integrity. Throughout the process, a high level of automation allows for efficient, repeatable operations, minimizing human error and maximizing productivity. The combination of welding methods ensures that each cylinder meets the quality and safety standards required for compressed gas cylinders. The aluminum radiator production process begins with flattening and cutting aluminum sheets to form the header plates. Simultaneously, thin aluminum strips are shaped into cooling fins through a fin-making machine. These fins are stacked and aligned between vertical tubes to form the radiator core. The assembly is then clamped and placed into a furnace for brazing, ensuring a strong bond between components. After cooling, side supports and brackets are attached. Each radiator is subjected to pressure testing in a water tank to detect any leaks. Following this, inlet and outlet fittings are welded onto the core. The radiators are then surface cleaned and coated for corrosion resistance. Final steps include visual inspection, bar coating, and automated packaging using protective materials. The finished radiators are boxed with foam inserts and wrapped for secure shipping, ensuring they meet ISO 9001 standards and deliver drop-in fit for easy installation. The Turbine Series 7000 is a high-speed bending machine that combines precision, performance, and ergonomic design. It is the first press brake with an ergonomic certificate, ensuring user-friendly and comfortable operation. Featuring advanced angle measurement systems like ACB wireless and ACB laser, it enables accurate, fast bending with up to 35% cycle time savings. The 6-axis back gauge enhances flexibility, while the TechZone Bend software and tool indicator simplify setup. With BendGuard Automatic and Mobile Control Pro, it offers safe, mobile operation. Compact yet powerful, it delivers top-quality parts in minimal space. The tandem hydraulic press system, equipped with a DA52 control system and an automatic front feed system, is used to form large street lamp posts. Initially, a flat steel plate is automatically fed into the bending zone. The synchronized Y1 and Y2 axes ensure precise and uniform movement of the two hydraulic presses, allowing for precise bending along the entire length of the plate. The steel plate is gradually bent as it moves forward, creating a conical shape which will produce different shapes depending on the desired pole design. The metal sheet is first positioned between the rollers of the bending machine. As the rollers rotate, they gradually bend the sheet into a curved shape through cold forming. The operator adjusts the roller pressure and position to achieve the desired radius and ensure precise, consistent bending throughout the process. The process of creating a flanged, flat bottom begins with a flat steel disc placed in a rim-forming machine. The edge is gradually rolled by rotating rollers to form a smooth rim of the required radius. The process continues until the desired rim shape is achieved, ensuring compliance with dimensional standards. The Roundo R62S corner roller can precisely bend metal bars into various shapes. 150 by 150 by 16 mm corners are bent to a diameter of 1,000 mm, while 150 by 150 by 15 mm T-shapes reach 1,200 mm. UPN sections, bent in a difficult way, reach a diameter of 9,000 mm. During operation, the shape is fed between 3 motorized rollers, with pressure gradually applied to achieve the desired curve, demonstrating fast, accurate, and heavy-duty bending capabilities. The setup process for the CTM automatic elbow machine starts by installing the bottom clamp using the dowel pin for alignment and tightening it securely. Next, the top and bottom plates are installed, ensuring they fit snugly and move within a 0.005-inch tolerance. Alignment is checked using a straight edge. Then, cutting and forming rollers are selected based on desired bead size. The cutting roller is adjusted to maintain a 0.001-inch gap from the cutting plate, using specific wrenches and torque settings. After reinstalling forming plates and inserting the tube, the one-cut procedure is performed to check for burrs. Finally, the oiler is set between 15 to 20 psi to ensure proper lubrication, and the machine can then run in automatic mode. The 408S 25-axis machining center performs high-precision milling and turning operations to machine a watch case middle. The process begins by clamping the raw workpiece onto a rotary table. The vertical spindle, capable of 30,000 revolutions per minute, mills various contours and surfaces moving along X, Y, and Z axes. Simultaneously, the B and C rotary axes reposition the part precisely, enabling complex angular machining. Fine drilling operations are carried out for future assembly points. Tool changes are automatically executed with high speed and repeatability. The double direct drive divider ensures angular resolution up to 0.0001 degrees, enabling flawless transitions between milling and turning. Throughout, integrated automation handles part positioning, ensuring consistent quality and efficiency. This process is ideal for producing intricate and high-tolerance watch components. The blade machining process begins with the use of a range of milling cutters, each designed for specific machining operations. The first is the roughing of the turbine blades using the Mill 600. This is followed by the Mill 390 and indexable conical ball nose tools, which are then applied to semi-finished complex shapes, such as housings and shafts. The Mill 216 and Mill Plura milling cutters handle the part shaping and 5-axis milling. The Mill 300 is used for efficient material removal, followed by the Mill 390 and Mill 316 for precise edge preparation. For finishing, the Mill Plura ensures superior surface quality. The Mill 490 supports grooving, while silent tools reduce vibration during the process. The combination of these advanced tools ensures high precision, optimal tool life, and excellent surface finish in the production of turbine blades. The titanium shoulder implant is fully machined on the NTX 1000 using 6-sided turning and milling. The process begins with rough turning of the cylindrical blank, followed by multi-face milling using simultaneous 5-axis machining. Complex contours are precisely formed by the direct drive motor in the B-axis, while high-speed spindles ensure smooth surface finishes. Final finishing includes contour refinement and drilling. The in-machine robot unloads the completed implant automatically, ensuring consistent precision and efficiency. The complete machining process using the M30 GMILLTURN begins by securely clamping the raw workpiece between the chuck and the tailstock. The turning spindle rotates the part at high speed, allowing for precise external and internal turning operations. With a swing diameter of up to 520 mm and a maximum machining length of 1,800 mm, the machine efficiently removes material to form the basic cylindrical shape. Next, the B-axis milling spindle, capable of rotating plus or minus 110 degrees, performs complex 5-axis milling tasks. The spindle executes contour milling, drilling, and tapping from multiple angles. Deep hole drilling is also possible during this stage. The machine's Y-axis movement of 250 mm enables offset operations, while the X-axis travels up to 600 mm for detailed profiling. Depending on the machining requirements, gear cutting may be integrated into the process using specialized tools from the 40 or 80 position tool magazine. The SINU MERIK 840D control system coordinates all axis movements with high precision. Throughout the process, the machine switches automatically between turning and milling tools, ensuring uninterrupted operations. The high spindles speed up to 4,000 revolutions per minute for turning and 12,000 revolutions per minute for milling, and powerful torque make the M30 GMILLTURN ideal for manufacturing complex shaft and chuck components in a single setup. The heavy-duty turning process begins with roughing and finishing operations on a large cylindrical workpiece. Throughout the process, an additional visual unclamping confirmation system is used. When the bar shows 0, the part is clamped. When it shows 5, the part is unclamped. These visual indicators ensure safe and accurate workpiece handling during machining. The machine performs surface milling and heavy milling to shape the external profile. Pocket milling and keyway milling are performed using interpolation techniques. Grooving is applied along the axis, followed by spherical grooving and spiral milling for complex shapes. The machine operates with high stability and torque to handle the demands of large-scale component production. The Gleason 1500G Titan gear grinding process begins with power grinding using a threaded wheel. The machine supports modules up to 14 with high tooth counts. Dressing of the threaded grinding wheel is performed on both the left and right flanks, with the dressing unit swiveling automatically. Coolant nozzles are adjusted precisely for threaded wheel grinding. Roughing then begins using a coarse grit threaded wheel to achieve high material removal rates. A gear with module 14, 84 teeth, 255 mm face width, and an 11 degrees helix angle is ground, achieving 36% time savings over conventional profile grinding. The machine features a fully automatic tool change system, switching between threaded wheel and profile grinding in under 1 minute. Up to 4 tool stations are available, with no interference risk between the tool and workpiece. For profile grinding, the dressing unit prepares the profile wheel on both flanks. Coolant nozzles are again automatically adjusted. Roughing follows with a coarse grit profile wheel for large gears, achieving 30% time savings. Finishing is performed with a fine grit wheel to reach surface finishes below RA 0.2, suitable for modules up to 44, ensuring the highest precision and quality. The assembly process of the Liebherr LTM 11200 begins with positioning the main carrier and deploying its outriggers for stabilization. The telescopic boom is then raised, and the counterweights are installed using an auxiliary crane. Next, the luffing jib components are delivered and laid out. Technicians attach the base section of the jib to the main boom, followed by intermediate sections, which are connected and secured with pins and hydraulic tools. The guying system is then mounted to support the jib. Rigging lines are threaded through pulleys to prepare for lifting operations. Finally, the fully assembled luffing jib is raised into position. Throughout the process, both the HB Kran and Franz Brocht units are shown working in coordination under Saren's supervision to prepare for windmill erection at the port of Rotterdam. Aluminum formwork systems are increasingly used in global construction due to their reusability, efficiency, and safety. The production process involves precision cutting, high-accuracy NC shearing, automatic bending, and welding using argon arc techniques. Each unit is polished, greased, and pre-assembled to ensure firm and reusable structure. Aluminum formworks help reduce labor, shorten construction cycles, and minimize waste. They can be installed quickly, reused over 200 times, and offer smooth concrete surfaces without plastering. With standardized metal components and professional 3D design integration, these formworks ensure consistent quality, environmental benefits, and economic advantages across high-rise construction and large-scale housing projects. Dunlop Aircraft Tires manufactures aircraft tires using advanced, semi-automatic equipment designed specifically for precision and efficiency. The process begins with layering rubber and fabric materials onto a forming drum, creating the tire's carcass. Components are carefully assembled to achieve the required strength, durability, and flexibility. Once built, the tire is placed in a mold and vulcanized under heat and pressure to cure the rubber and shape the tread pattern. Strict quality checks follow, including visual inspections, air leak testing, and non-destructive testing such as shearography. The company's flexibility in small batch production allows rapid adaptation to customer needs. Dunlop also focuses heavily on retreading. Worn tires are returned, tested, and given new tread layers to extend service life. The entire process is supported by continuous R&D, enabling Dunlop to innovate lightweight, high-performance tires with increased landing cycles and foreign object damage resistance, ensuring world-class quality and safety. The rubber mixing process begins by feeding the pre-mixed rubber compound from the internal mixer or Banbury into the rubber mixer. This can be done via an automatic feeder. The compound is placed between two rotating rollers where it is flattened and formed into a sheet. Initially, the operator collects the fallen rubber lumps and reloads them between the rollers. The clamping gap is adjusted throughout the process, starting wider and then decreasing as the compound becomes more homogeneous. As the rubber sheet forms and rolls evenly over the front roller, additional ingredients such as sulfur and hardener are added. These pre-weighed materials are thoroughly dispersed by rolling, cutting, and folding the rubber sheet repeatedly through the rollers. Any loose pieces are reloaded to ensure uniformity. Once a homogeneous mixture is achieved, the sheet is cut to the specified size, dipped in a release agent, and air-cooled. Finally, the plates are marked with batch details and stored. Throughout the process, the operator must ensure safety and accuracy to avoid compound rejection and must record production details in the report. The production of rubber mat rolls begins with breaking colorful EPDM seal strips into fine rubber crumbs. These crumbs are then sifted through a screening system to remove any impurities, such as dust, fibers, or oversized particles. Once cleaned, the colorful rubber crumbs are poured into a high APA city industrial mixer. In the mixing process, 8 kilograms of rubber crumb are combined with 1 kilogram of polyurethane binder. The mixture is blended thoroughly for about 8 minutes to ensure an even and consistent distribution of the binder throughout the crumb material. Uniform mixing is essential to guarantee the final mat's durability and performance. After mixing, the crumb binder mixture is manually filled into a large mold. Within 15 minutes, the mold is completely filled. The material is then subjected to hydraulic pressing, which applies high pressure to compress the mixture firmly. Once the pressing is complete, the mold is fixed in place and left to cure for 24 hours, allowing the rubber to vulcanize and solidify into a dense column. The cured rubber column is then removed and placed onto a whirling machine for cutting. A new diffusion knife is used for each column to ensure precision. The cutting distance is adjusted to produce rolls of various thicknesses. The cutting operation is fully computer controlled to achieve high accuracy. Next, the rubber sheets are cut into lengths according to customer orders. The first and last portions of each roll are trimmed to ensure clean edges. All rolls are measured and cut precisely to maintain consistent size. Finally, the rolls are tightly wound, printed with product information, and carefully packed for shipment. During the vessel's scheduled 5-year docking in Sweden, Hafter and Corona Seaways underwent a comprehensive upgrade. The process began with the removal of rope guards, zinc anodes, and old propeller blades. Flow-optimizing rudder bulbs were welded onto the existing rudders, and propeller fairing cones were installed on the hubs. New high-efficiency CLE propeller blades were then mounted. Additionally, the variable frequency drive system was installed, including power converters and transformers, and the Alphatronic control system was upgraded. These enhancements enabled variable shaft alternator speed, improving efficiency at part load, while still maintaining 20 knots when needed. The 35-meter-tall wind turbine tower is transported along a narrow, winding road that requires precise control. The long cylinder, mounted on a multi-axle trailer, navigates the tight bend with the help of a steering shaft and a spotter on foot. The driver carefully adjusts the truck's position, frequently backing up and realigning to negotiate sharp turns without damaging vegetation or roadside structures. On certain bends, the rear trailer wheels are actively steered to follow the path of the front wheels. On extremely tight bends, the truck crawls forward inch by inch, guided by crew members giving the go-ahead. Trees and signs are narrowly avoided, and the convoy stops to reassess the angle and alignment. The narrow road, with no room for error, requires complete coordination between the driver, escort vehicles, and ground crew. This meticulous approach ensures the giant tower passes through the complex road geometry without incident. Shredded tires are fed into the reactor, heated anaerobically to produce oil, carbon black, steel wire, and gas reused for combustion. The process of making colorful spun bamboo bowls begins with harvesting old bamboo trees, which are then transported and split in half. The bamboo is soaked, dried, and further separated into thin strips by hand and machine. These strips are planed to create uniform thin layers, which are woven into bowl shapes using traditional techniques. After weaving, a base enamel layer is applied and left to dry. The bowls are then ground to smooth both the inner and outer surfaces. A second enamel layer is added inside for protection. Finally, multiple coats of colored paint are applied, with light sanding between layers for a flawless finish. Each bowl is marked with hand-printed paint, completing the process for export. The process of making a wooden barrel begins with the cutting and sawing of the wood into smaller pieces, which are then planed and beveled into long and narrow strips. These are arranged lengthwise in a circle and are temporarily held together with a metal ring. The craftsman taps the strips with a hammer to ensure proper alignment. The partially assembled barrel is then heated over a fire to make the wood more pliable. Once heated, a press is used to pull the strips tightly together. Metal rings are hammered into place to secure the structure. The mouth of the barrel is smoothed with a grinder, and the entire surface is refined with a hand plane and a paring knife. Particular attention is paid to the base, where a specialized paring knife is used to ensure a precise and smooth surface. This meticulous process ensures that the barrel is both durable and well crafted.